So thank you for joining us today. I'm your host, Leah Roslin, the online editor for BioProcess International. And before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted our audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions. Your questions in the question and answer window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Michael Bransby from Repligen.
Greetings. Thank you for joining me this morning for a short webinar. My name is Mike Bransby, and I'm the R&D Director for Filtration, working primarily out of Repligen's Southern California office in Los Angeles. Our topic today is centered around increasing bioreactor productivity of lentiviral vectors for gene therapy applications, which was done in partnership with Oxford Biomedica using a very new filtration technology called Tfdf. This is just one application of this technology, and we don't have a lot of time together today, so I'm going to focus on the yield benefit and then describe in general terms that the technology is fast, requires a very small footprint, and is operational simple even at larger scales. If you'd like to learn more about how the technology works or other applications, I encourage you to contact your local Repligen sales representative or visit repligen.com. The title of the webinar, which is rather long, so I'll try to get it in one breath, is 2.5x lentiviral vector bioreactor yield increase and simplified execution with innovative tangential flow depth filtration. So, mouthful. Next slide, okay. As we survey the viral vector workflow, Repligen has developed and launched many solutions to help with different pain points. If you're looking for a faster, better way to complete your unit operation or analytics, give us a call. We're working on these things all the time. Today we're focused on viral vector production and the clarification steps, so the ones outlined there. There are some clear needs in the industry. I've been in the gene therapy area for over 15 years, and the harvest step and getting more virus produced has always presented specific challenges. So, can we get increased viral vector yield with gentle methods that are lentivirus compatible in a closed aseptic format? Hopefully, you'll see we're addressing several of these needs with the new Tfdf technology. So the case for an increase in viral vector yield is supported by a model built and published by Renninger and others in December of last year. So their model incorporates the number of active clinical trials, phase 1 through phase 3, average yields, and requirements per indication to create a plot of the number of batches required per year. So, gene therapy is going exponentially, and you look at the different models they have with different capacity growth, they're still linear. So we're all in quarantine, and everyone says flatten the curve. Well, we don't want to flatten the gene therapy curve going up exponentially, right? We want to meet that curve. We want to get technologies to enable us to support, the incredible growth and promise for therapies in the gene therapy area. So, but both models that they have here conclude total demand will exceed total capacity even this year in 2020. So really that's the pain point we're looking to address. So Oxford Biomedica was the first to develop a commercial lentiviral-based gene therapy gene delivery system, and they've transitioned their adherent HEC-293 cells to a suspension bioreactor in order to increase yield. Repligen is a leader in high-impact bioprocessing technologies, the latest of which is Tfdf, or Tangential-Flow Depth Filtration. Tfdf is the first depth filter that runs in tangential mode. In order to accomplish this, so we look at the graphic here, the filter is tube-shaped, so it's a tubular depth filter and not dead-ended. In this picture, we have a bioreactor that contains the blue HEC293 cells and orange lentivirus particles. So the cell culture fluid travels down to the pump, goes through the lumen of the tubular depth membrane, and then back to the reactor. So what's really important is to understand most of your solids are not getting caught up in the filter. They're going back to the reactor. This also shows an integrated system. It has pumps and software. It's an automated process. All of your components of sensors, your pump, your flow path comes ready to use, gamma irradiated. So this brings us to two key questions raised when Repligen's Tfdf technology met Oxford Biomedica's suspension culture. First, can Tfdf improve the harvest unit operation over classic depth filtration? Second, because the cells are preserved, can they be used to create more virus in a high productivity mode, which is also frequently referred to as batch perfusion? You can read about the details of the work in the Cell and Gene Therapy Insight article published just a few months ago. The first experiment is a straightforward comparison of Tfdf and depth filtration at the 5-liter scale using a therapeutic lentivirus. When normalized against bioreactor titer, depth filtration delivered a yield approximately 70%, and that's in the red and the salmon. Tfdf, in comparison in the blue, delivered a yield greater than 90%. So clearly the Tfdf transmits the virus. So why the increase in yield? Several reasons. First, the nominal pore size, the pore rating of the Tfdf filter is 2 to 5 micron, meaning that while holding back the cells, the 100 or 120 nanometer size lentivirus has plenty of room to navigate the channel through the wall. Second, that the filter material, which is completely synthetic and built primarily of polypropylene, does not bind product. Third, why does the virus pass? Because of the high capacity. So a Tfdf is more than 10 times smaller than a depth filter and therefore has very low holdup volume. So together, they more effectively separate the cells from the product. So I want to show you a graph that brings out the advantages of Tfdf filtration in a bit more detail. X-axis of the plot is time. And then we have two different y-axes. The first is pressure and the second is flux. So Tfdf typically delivers flux rates up to 10 times greater than depth filtration. In this example, the flux starts at 750 LMH, which is really high compared to standard hollow fibers or even depth filters. And it remains stable at that value over the course of the entire run. On the left axis, let's look at TMP. In contrast to a dead-end depth filter, Tfdf directs the majority of the cells away from the filter, back into the reactor. So it's not getting trapped in the filter. So the product and the cells are not competing for access to the same channels. And the system becomes very robust to fouling. TMP for the run starts at very low value of 0.5 pounds per square inch and increases only 0.25 psi. There's essentially no fouling going on. So the last thing we want to show you, the advantage here, is time. So if you look at the x-axis, with a flux of 750 LMH, the operation can be completed very quickly. In this example, 5 liters was clarified using 50 square centimeters in less than 1 hour. To put that in perspective, the filter for 5 liters is about the area of the palm of your hand. So the combined depth filter with Tangential-Flow enables it to process very quickly and be that compact. Let's take it one step further. So Tfdf can return the cells to the reactor and does not foul, which begs the question, is this process gentle enough to reuse the cells? So we're all in quarantine. Everyone seems to be making bread. There's no flour available at the store. My wife is making many batches of sourdough, and she keeps the starter, and she's able to feed that starter after she uses it to get another batch. So can lentivirus production be running the same type of high productivity harvest, or a batch perfusion mode? Can you keep it going? And the answer is yes, and this is what this slide shows. Using a 5-liter sub and an HIV GFP virus, first harvest was executed at 750 LMH, delivering a yield on the bar graph greater than 90%. Fresh media was then added to the bioreactor, cultivation was continued, and a second harvest was executed, once again at 750 LMH. So the yield for the second harvest was 85%. So let's do a little math. Let's add up the numbers. If you combine the first and second harvests, and you obtain harvest yield of 170%, divide that by the 75% from the depth filter, and we see about a 2.5x more material generated. So really powerful. We're able to get almost more than double the capacity from the same reactor. So granted, some additional tests are taken, more media, but the value of the 2.5 increase should far outweigh that effort. So from a technology level, the low shear rate of Tfdf preserves the integrity of the HEC-293 cells even when operating at really high fluxes, enabling altogether new lentiviral bioreactor applications. So earlier I showed you the graph before of one harvest of pressures and flux versus time. I want to show you the exact same graph here, but for these two harvests that we just described. During harvest 1, here we ran at 700 LMH. The TMP increases less than 1 PSI. Again, essentially no fouling. So over the course of the second run, it rises a bit, but still only to 2 PSI. Therefore, both harvests are completed with the same filter with a total of less than 3 PSI increase. It's important for me to mention that the flow path that surrounds the filter is closed gamma radiated, which is a key enabler of these multiple harvests. That is, you connect to the reactor, it's a closed system, enabling you to do this. We can essentially make the connection of the Tfdf to the bioreactor and process over extended time periods with negligible contamination or bioburden risk. So does it scale? All of the runs we looked at so far have been at 5-liter scale. Are we able to show this same performance at larger scale? So we scaled the 5-liter tenfold to the 50-liter scale reactor and found that yield, process time, filter fouling were very similar to the 5-liter scale. The yield showed greater than 90% again. The flux was constant at that 750 LMH. TMP ended below 1 PSI. The operation again was wrapped up in less than an hour. So Tfdf filter sizes are available in even larger sizes, and we can get bigger pumps and bigger tubing such that volumes of 200, 500, 2,000 liter are also feasible. So yes, it does scale, which is great. But the bigger we go in scale, the more challenging the operation becomes. Anybody can process small scale. It's pretty simple. But as to go to larger scales, it's really where the rubber meets the road and where Tfdf really shines. Therefore, I just want to walk through what Tfdf looks like if we were to scale another tenfold from 50 liter to from 50 to 500 liters. So we scale the Tfdf process by adding more filter tubes to the enclosure. This means that the simplicity of Tfdf carries from 2 liters to 50 liters to 500 liters and beyond. Each of these scales, you only have one device to unbox, install, and break down. Assembly, disassembly are completed in 20 minutes. So it's 2-liter scale, 500-liter scale, with only 3 connections using genderless aseptic connectors. All the pressure sensors, the magnetic pump head, are built into the flow path. And in terms of space, the entire footprint of your skid is only about 10 square feet. This is because the filter mounts directly onto the skid with the pumps. It's really, really simple. And that simplicity scales all these different volumes. So there's no need to organize 20 different parts during setup. There's no Wi-Fi flush. The filter ships dry. There's no product flush. There's no product mess spilling out during the breakdown. There's no hardware dedicated just to holding the filter. So that core concept of combined depth and tangential flow filtration create capacity and volumetric throughput that delivers more product much faster in a much smaller footprint than classic depth filtration. So really advantageous. So I'd love to dive deeper into the technology and its other applications, but I'm going to have to wrap it up with this slide that simply describes the different components that work together to create this complete solution. So it starts with a tubular depth filter, the first depth filter to act in tangential mode. We then integrate the filter into the flow path that includes the filter, tubing, clamps, pressure sensors, so on, pump heads. So the beauty is that at the small scale, you only have one device in box, like we described, install and break down. And then at the large scale, you still only have one device to unbox, install, and break down. The ProConnect flow paths are all closed and gamma radiated, and they come as both stock, off-the-shelf, and configurable models. The final component, the final component to the solution is the system, which includes automated process control logic, specifically engineered for Tfdf. Tfdf systems like the flow path scale from the lab to the pilot and process scale. So I just want to thank the contributing authors at Oxford Biomedica, specifically Thomas Williams, Oliver Goodyear, Lee Davies, Carol Nevelman, Kyriakos Mitrofanous, James Miskin. It was a great collaboration. And finally, thank you for taking a few minutes out of your busy day to join us here at Repligen for this webinar. If you're interested in learning more about Tfdf or exploring new applications of the technology, please reach out to your local Repligen sales representative or visit repligen.com/Tfdf to start a conversation. Thank you so much for joining us.
Okay, great, Michael. So we have some questions. The first question is, can the application be extended from lentiviral vectors to AAV?
So it's a great question. We're exploring that area currently, and so if you're interested, please contact us. But there's some potential definite applications in that area, but yes, we are exploring that.
Okay. And is it possible to use Tfdf for clarification and not run multiple harvests?
Yeah, so the first slide that I showed was just compared, just clarification to depth filter clarification. And it showed 70% or about for the depth filter and 95% on the Tfdf just for a batch clarification. So yes, it is very possible just to do the batch clarification as well.
Okay. And I run TFF on a regular basis. How similar is the process to HF or flat sheets?
So Tfdf runs almost the same as a hollow fiber system. So you just have recirculation with a pump and pressure sensor. So it's very similar to the setup. There's just a few tweaks here and there as we optimize the technology that sort of enable this really high flux. But it's very similar to TFF setups. Excuse me.
Okay. So Michael, let's do one more question from the audience. Is the Tfdf operated in a unidirectional flow mode, and how does the depth filter react on backflashes?
Yes, great question. So this design is a unidirectional flow. So it's a standard TFF operation. So there's not an alternating flow. There's also exploring that area as well. But we don't recommend a backflush as it is a depth filter. So things get caught in there. We're not doing any backflushes to flush the filter. We get really high fluxes and really good volumetric throughput with no permeate backflushes.
Okay, great. Well, I think that is all the time we have for today. And again, we will be sending Michael your questions. So if we didn't get to your question, there are a number of you we didn't get to those. We will be passing those on to Michael, and he can follow up with you directly. As a reminder, the recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Bye.
Bye. Thank you so much. Bye-bye.